welcome to RECTV Education viewers once again. In this session, we are going to work out some numericals based on the concept of boundary conditions. Now, before going to numericals, let me explain you the procedure to be adopted for working out the numericals on boundary conditions. So, as in the previous classes, already I have derived these expressions. ET1 is equals to ET2 and HT1 is equals to HT2. These two are the tangential components in electric field and magnetic fields. Okay, and consequently, coming to the normal components, the field density, flux density vectors are equal. That means dN1 is equals to dN2. So coming to the magnetic field, Bn1 is equals to Bn2. So these are the boundary conditions in the electric field and magnetic field respectively. Now the supplementary equations are the relation between E and D is, we all know that D bar is equals to epsilon into E bar and B bar is equals to mu into H bar. So what is D here? D is the electric flux density vector and E bar is the electric field intensity vector. Coming to B bar is the magnetic flux density vector and H bar is the magnetic field intensity vector. Okay, so these are some of the basic relations you should know before working out some numericals on boundary conditions. Now, let me explain you the concepts, the procedure to be adopted for determining the unknown components in terms of the known components. Now, let me say he might have given you B1. Okay, so that means what I meant to say is, basically he'll be specifying a boundary condition. So how he specifies the boundary condition? He may say that x-axis is acting as the boundary condition, or he may say y-axis is acting as the boundary condition, or sometimes he may say that the z-axis is acting as the boundary condition, boundary. So if x-axis is acting as the boundary surface would be along yz plane. So for this case, the boundary surface is lying in which plane? In yz plane. Okay. Similarly, if y-axis is the boundary between the two dielectrics, then the boundary surface obviously is lying in, if y-axis is the differentiating axis, obviously the boundary surface is along z-axis plane. Okay, similarly, if z-axis is acting as the boundary, then simply the boundary surface would be lying in simply xy plane. Okay, so this is how we'll come to a conclusion, which is the in which plane the boundary surface is lying. Okay, so when x-axis is dividing the two dielectrics, then the boundary surface is lying along yz plane, and similarly the remaining two. Okay, now after identifying what is the surface, what is the plane which is containing the boundary surface, next is we need to determine its normal component A and cap. Okay, so what is a normal component? So normal component will have two types actually. One is the plane boundary. Okay, so for plane boundary we are going to specify the plane boundary. That means the equation of the plane will be given to you, and coming to a simple boundary, it will be either of these three. So one of the axis will be acting as the boundary, and the plane will be either of these three planes. So depending on which is the type of the boundary surface, we can determine the normal vector, unit normal vector. Okay, now let me explain you how can we determine the normal vector, normal component. So for example, B1 is given for us. Let me say B1 is given for us. So if B1 is given vector for us, then it can be written as, it can be split into two components. What are the two components? One is the tangential component, we'll write it as BT1, and the normal component as BN1. So BT1 is a tangential component of B1 and BN1 is a normal component of B1. Now, how to get this normal component of the given vector is the basic formula is BN1 that is the normal component, is always equals to the original vector, given vector into the unit vector. So it is simply an1. So b1 dot an1. That means it is a dot product of b1 and an1 into an1. Okay, so how to get bn1, the normal component of the given vector? It is simply original vector, the original given vector dot the unit vector, that is the unit normal vector, into the original normal vector. Okay, so this concept you can easily understand when we do one numerical. Now, how to get, this is the relation to get the normal component. How will you get the tangential component afterwards? Simply bt1 is from this equation. If you observe from this equation, bt1 would be b1. Of course, here both are all are vectors. So b1 bar minus bn1 bar. So the normal component, once it is determined using this relation, I can determine the tangential component by using this relation. Okay, once we got bn1, and bt1. Okay, so using these relations, I can get once I know bn1, I can get easily bn2. Why? Because these two are directly equal. And coming to bt1, so if I know bt1, how can I determine bt2? So from this, how to determine bt2? Then for determining bt2, I'll go with this equation. So I'll go with ht1 is equal to ht2. Now ht1, I can replace it with bt1 by mu1. How can I replace it here? Because b1 is equals to, b equals to mu into h. So if I know b, then h is nothing but b by mu. So I can replace h with b by mu. So ht1 can be replaceable with bt1 by mu1, and that should be equals to, of course, mu1 into mu naught, where mu1 is the relative permeability of that particular medium. So bt2 by mu2 into mu naught. So mu naught gets cancelled. So how to get bt2 from that equation? So if you observe this equation, bt2 is simply mu2 by mu1 into bt1. So once you determine this bt1 using this equation, so using this equation, if I am determining bt1, substitute in this, we will be getting the value of bt2. So the basic funda here is how to determine normal component of the given vector. So that is the basic rule. So I mean basic concept. So using this relation, how to get the normal component? The given vector dot product of the normal unit vector into unit vector, that would give you your the normal component of the given vector. Once you determine the normal component of the given vector from the original vector given, you just subtract the normal component, that will give you the tangential component of the given vector. So once you segregated the tangential component and normal component, the remaining process is only using these two equations. So using these two equations, we can manipulate and we can get the remaining wanted components. Now once we determined the unwanted, once we determined the bt2 and b and 2, simply b2 would be bt2 plus bn2. So bt2 is known by this relation and bn2 is known by this relation. So by this relation, we are going to determine bn2. So knowing bn2 and bt2, just substitute in this relation to get the vector b2. So now finally we got b2. Now what is the next step? Actually, we are going to determine the angle theta, which is the angle made with respect to the unit normal. So now if I want to determine theta 1, what is theta 1 actually? Now let me explain you what is meant by theta 1. So theta 1 is the angle made by the resultant with respect to normal to the made by the resultant field, maybe E or D or H or B. Okay, so with respect to the normal to the boundary surface. Okay, similarly, what is theta 2? I mean, these are all ones, E1, H1 and B1. And what about theta 2? Same angle made by the resultant, of E2, D2, H2 and B2 with respect to normal to the boundary surface. So let me explain you how to determine this theta 2 and theta 1. So simply the relation to determine theta 1 is simply the theta 1 is given by tan inverse ET1 by En1, as simple as that. Tan inverse ET1 by En1. And what about theta 2? Theta 2 is tan inverse ET2 by En2. Now if you know ET1 and ET2, you can substitute directly here. Or if you know D vectors, that means if you know the tangential component of D and normal component of D, then it's just replace E with D. So it is tan inverse dt1 by dn1, and here also it is tan inverse dt2 by dn2. Okay, so these are the relations to determine theta 1 and theta 2, where theta 1 is the angle made by the resultant field with respect to the normal to the boundary surface. Now, if I wanted the angle with respect to the boundary surface, so in the question, if he is asking you to determine the angle with respect to the boundary surface itself, then just let us represent it as alpha 1. So what is alpha 1? Alpha 1 is the angle made by the resultant field with respect to the boundary surface. So for example, if this is the boundary surface, and let me say this is E1, so so this is the normal, so this angle is theta 1 and this angle is alpha 1, so this is your boundary surface. Okay, so how alpha 1 is given from this figure? Simply 90 minus theta 1. Similarly, if I say that this is the E2, electric field intensity E2 in the second medium, then this is alpha 2 and this angle is theta 2. So if you observe, what is theta 2? Theta 2 is the angle made by E2 with respect to the normal. And what is alpha 2? Alpha is the angle made by E2 with respect to the boundary surface. So from this figure, alpha 2 I can easily write it as 90 minus theta 2. Okay, so now let us apply these formulae for doing one problem, and that will give you more exposure of this concept.